Okay, everyone, welcome back. This is the third and final video for discussion of the homework on section 7.2, the dot product. Let's get right into it. So, question 9. This question asks us to compare the vectors s and t. And 3, 7. So what jumps out at me initially is that I think they're orthogonal. So I think S is orthogonal to T. Now, why do I think that? So we have to go into a little analogy here, or a little a side discussion, I guess, on slope. So S, the vector 7, 3, you can think about it as this being the run, the change in the x component, and this being the rise, delta y. So then as its analogous slope, in a sense, would then be -3/7. Okay, what about t then? T is the vector 3, 7. And again, we have the same comparison we can make. This is equal to a run. This is a rise. Delta x, delta y. And then this vector, let's call this m1. Its equivalent slope, in a sense, would then be 7/3. Okay, now notice something here. M1 and M2, if these were lines, these would be two lines that are orthogonal to each other, because each of these is a negative reciprocal of the other. Negative reciprocal. That's a fancy way of saying take the fraction, flip it, and once you flip it, add a negative sign. So if they're negative reciprocals, a line 1 with m1 slope, line 1 with m1 slope, is perpendicular to some line 2 with m2 slope. So that's the connection that you should make here with the vectors s and t. Now, that's long-winded, and maybe you didn't catch all of it. So an easier way, in part B, asks us to verify our hypothesis using algebra, an algebra construction or logical argument as appropriate. So the easiest logical argument that always tells you about angles is the dot product. So the dot product is amazing at picking out angles. It's the key thing we'll use again and again and again, pretty much. So S dot T well, that's equal to 7 -3 which is 7 times 3 plus -3 times 7, and that's 0, which is what we expected. That means S and T are perpendicular to each other. This symbol just means perpendicular. Okay, good. It's question 9 done. Well, question 10. So for question 10, we're actually going to use the same reasoning we did for 9a. Find a vector that is perpendicular to u. 9, 2. Well, a vector perpendicular to u, the dot product with whatever vector it is, must be 0. And I'm going to say the vector v, again, if I think of this as a run and this a rise, then -9, sorry, -2, 9 should be perpendicular. So let's check. U dot v 9, 2 dot -2, 9. And we get 9, -2 plus doing component-wise multiplication, 2 times 9 gets 0. All right, so that's same reasoning I used as in 9a to solve 10. Okay, moving on to 11. The next two are quite simple. Determine the value of k so that u and v are perpendicular. So for u to be perpendicular to v, it requires u dot v to equal 0. Okay, so then this condition now leads us forward. We have 2, 5, and k4. Dot k4. Okay, so then we get this dot product is equal to 2k plus 5 times 4, which is 20. And we're saying that it must be equal to 0. So, how should I do this? I'm going to erase this. Two 5k4 2k plus 20 equals 0. Okay, and that means k is equal to minus 20 divided by 2 is just 10, minus 10. So that is our correct value for k. So if we plug that in for the x coordinate of v, we should expect that u and v are perpendicular. Okay, 12. Same reasoning. Determine the value of k so that u and v are perpendicular. So again, for u to be perpendicular to v, it requires u dot v to equal 0, which means u dot v equals 0. So u in this case is k3 and k2k. Okay, so then we get k squared plus 6k, just using component-wise multiplication, then adding. But then we can factor the left-hand side as k plus 6 equals 0. So that means the value of k equals 0 and k equals -6 should satisfy this equation. But that means if we plug in any of those values for the x component of u, or the x and y components of v, in this case, we should expect that the vectors are perpendicular, u and v. That's all. This last breakdown of the homework is quite easy, so I hope you can now finish it all, and best of luck. Have a great day, guys.